Welcome back, class. So last time we learned about that if we have a magnetomotive force, then what is the relationship between magnetomotive force, flux, and the reluctance of the core. And we have learned the relationship between relative permeability, magnetic flux density, magnetic field, relationship between the relative permittivity and the permeability of the material and the free space permeability and the different more examples. And then we will solve different examples relevant to that. So we have noticed one thing that the generated flux in a core, okay, is basically depending on the permeability of the material, right? What is the relative permeability of that material? For example, if we have air gap, its relative permeability is different, so its generated flux or reluctance is different. If we have the core material, it's different. So basically the properties of the material in terms of its relative permeability characterize the performance of the material. Okay, so with that we also have some losses which are associated with the properties of the material. Okay, so here first we are going to look into those losses, that what are those losses and how those losses occur. Okay, so basically there are two types of energy losses: basic hysteresis loss and the eddy current loss. So we are going to see everyone. Okay, so basically what is happening, for example, let's say we are supplying this input. Okay, this is sinusoidal input current and we are supplying this to the core of the material, and we want to analyze that for example, due to this, of course, the magnetomotive force will be generated, okay, which is n times of this. Okay, and then we will have the flux because of that and reluctance, right? So let's say this is the flux or applied H field, and this is the magnetomotive force, and this is the flux or the magnetic flux density. So when we actually apply the input current, okay, and if you apply a large like if we are increasing the magnetomotive force, then the generated flux will actually follow this path. Okay, generated flux, let's say initially it's 0, it will go like this and it will reach this path B. Okay, and now what is actually happening, okay, inside of the material, okay, we actually have different domains. Okay, so basically when you are applying, so this is the internal magnetic field within different domains, so small regions which we call domains. So this is the orientation of the magnetic field in different regions. Okay, so when we are actually applying this large electromagnetic magnetomotive force, okay, so basically we are getting higher flux because of the alignment of this internal magnetic field. Okay, so when we apply high magnetic field, so these electromagnetic fields, they will be aligned, okay, to that. Okay, for example, this is the original random orientation, and in the presence of the external magnetic field, they will try to align with that. Okay, they will try to align with that. So let's have a look at this picture. So initially what is happening, okay, let's call this is A and B. Okay, when we apply the electromagnetic force, initially they have random nature. Okay, and as soon as we are increasing the magnetomotive force, they are trying to align with that. Okay, so maximum, when we get the maximum alignment, after that, okay, that would be the maximum limit of the flux which we can get. Okay, now if you are removing the external magnetic field, okay, for example here you have applied this much magnetomotive force. Okay, now you are removing that. Okay, so ideally what should happen, okay, the return path should be this. Okay, but what is actually happening here, that it will not be the return path. Okay, why? Ideally, when you remove the electromagnetic force, they should go back to this random orientation also. Okay, but not all of the domains. Okay, they will be gone back to the random. Okay, some of them will be gone back and some of them will not. Okay, So we will reach this point. Okay, we will reach this point. Okay, now what is actually happening, although you have made the magnetomotive force 0, but still there are some regions which are aligned, means there is some flux, residual flux, remaining flux inside of the material. Okay, now to make that flux 0, we have to apply, like we have to do the random orientation, we have to remove the alignment of that. So we apply some external more negative magnetomotive force so that they should be disaligned at this point. Okay, now to make it 0, okay, to get this thing we have to apply some more magnetomotive force, so that we get this one. Okay, and eventually we increase more negative magnetomotive force, so these domains will be aligned in the other direction. So here they were aligned in this direction, now they will align in the other direction. That will be the maximum flux which we can generate in the, so when we achieve the alignment, that is the end. That is the end. Okay, that is the maximum flux that can be generated. After that, even if we apply more magnetomotive force, there will be no generated flux because the alignment has been achieved. Okay, now from this point again, if we increase the magnetomotive force, okay, first we will reach this point, half almost some of them lose the orientation but some not, so we have residual flux here. Okay, then we apply some more, it becomes 0 here, we get the all not aligned here. Then if we further increase, we get the more alignment here. Okay, the all of the domains are aligned in that particular direction. Okay, so this is the map which we are getting. Okay, so this is called hysteresis. Okay, this is called hysteresis because based on the shape. Okay, so basically what is happening, when we are applying some magnetomotive force, eventually we are getting the maximum flux due to the alignment. Okay, due to the alignment. Okay, and if we are removing that, still we have some internal flux which is there. Okay, which is actually basically the loss. Okay, we want to make the total disalignment, but still some of the domains are not totally disaligned. So there is some residual flux. Okay, flux is 0 here, so there is some residual flux here, so that residual flux is basically the loss. So that could be the loss which the core, the material, could face because of the hysteresis, because of the alignment and disalignment of the domains of the electromagnetic field. Okay, because of the changing flux. So the other one is the eddy current loss. Okay, so I will explain the eddy current in after a couple of slides. Okay, so these two losses are basically related to the core of the material. These are the material properties, external losses of the material. Okay, so if we characterize external losses of the material, it will be hysteresis loss and the eddy current loss. Okay, we will learn about eddy current soon. Okay, so these two losses can degrade the performance of the core of the material. So these are called external losses, and another name of these losses is core losses because they are associated with the material properties. Next is Faraday's laws. So we have learned that if the flux is changing, okay, for example, if this is one coil and this is the second coil, okay, so if the flux is changing, so the changing flux, okay, it will induce a voltage in the second coil. Okay, so the rate of change of flux, it will induce a voltage. Okay, and the direction of the voltage will be negative because of the Lenz's law. Okay, Lenz's law says that the direction of the induced voltage will be opposite of the changing flux. Okay, this is the Faraday's law which we have learned earlier on. So it's just a review. Now if the coil has n number of turns, then the generated flux will be n times of the individual. Okay, so just the general equation for the Faraday's law. Okay, if they have n coils, it will be n times of the changing flux. Okay, so what we have learned from this, what Faraday's law is telling us, that if you have a changing flux through a region, okay, if you have a changing flux through a region or through a coil, okay, then for example, let's say this is a wire, this is one wire, and through this wire, this is the magnetic field, for example, and this is changing, the flux is changing, so that will induce a voltage across this wire. Okay, and that voltage we represent using induced voltage. Okay, so the changing flux will induce voltage. Okay, so if we have a short circuit here, then the current will start flowing through this. Okay, so this is the Faraday's law. Okay, now if you remember the hysteresis, okay, so when we are having the alignment, we have the changing, like we are increasing the magnetomotive force, we are getting more and more flux, then we are decreasing the magnetomotive force, we are getting lower and lower flux, so the flux is changing. So this changing flux will actually induce the voltage within the domains, okay. So this changing flux will induce the voltage. Okay, so when the voltage is induced, so the current will start flowing. Okay, so when the small current, this is very small current, okay, this is very small induced voltage, okay, when this small current start flowing, okay, so then what will happen, to your core, your actual material of the transformer, it will start heating up. Okay, so basically we got heating losses, okay, which are basically I square into R, the internal resistance of the core multiplied with this current which is being generated. So this current is called eddy current. So the current which is generated due to the changing flux, okay, inside the core, not outside of the core, inside the core, due to the alignment and disalignment of the domains of the core. Okay, this is the eddy current. How we can reduce that, we will learn this in the live session. Okay, about the direction of the flux, I will explain in the live session that how we can actually calculate the direction of the flux and the other things. Transformer, we know that the transformer have two terminals, the input terminals and the output terminal, or primary terminal or the secondary terminals. Okay, and the general rule is the changing flux. Okay, if you are supplying current here, so here we are having the change of flux. So this change of flux basically induces the voltage at the second end. Okay, so induced voltage is n times of the rate of change of flux. So if we have n number of turns here, then the rate of change of flux is basically the ratio of the input voltage divided by the input number of turns, or output voltage divided by the output number of turns. Okay, so basically this primary side current, okay, it will induce the flux, and the rate of change of flux will induce the voltage at the secondary terminals. So this is the general formula of the transformer working. So eddy current, as I have explained earlier, okay, inside the core, the small current will start flowing, okay, inside the domains, okay, and that will induce the heating losses. How we can reduce, we will see in the live session. Example solved in the live session. The last thing, production of the induced force on a wire. Okay, so we have learned that if the flux is changing, it will induce a voltage, okay, in the wire. For example, if a wire is present in that changing flux. So another effect of the magnetic field is that it will induce a force on a current carrying wire. Okay, so for example, this is a wire and the current I is flowing through that. So if this current is present in a magnetic field region, okay, so these are the magnetic field region. This cross shows into the page magnetic field. So if we have dot, that will tell us out of a page. Okay, magnetic field. Okay, so if a current carrying wire is present in a magnetic field, that current carrying wire, so basically due to the effect of the magnetic field, it will experience a force. Okay, it will experience a force. So force is actually represented by the current carrying wire, the current, and the cross product of the length of the wire with the magnetic field. Okay, cross product of the length of the wire with the magnetic field. Okay, or we know that L cross B will be basically LB into sine of theta. So theta is the angle between the wire and the B. Okay, so what is the angle between the wire and the B? Okay, that is the angle of theta. Okay, so this is basically the basic effect, another effect of the magnetic field on a wire which is present. Okay, so we can actually find the direction of the force, that which direction. Okay, either like in this direction or it's in this direction using the left hand rule. So I will explain this about this finding of the direction of the force in the live session. Okay, that's it for today, this lecture. Thank you very much for your time, and we will solve the relevant examples about this in the live session. Thank you.